for the second lecture of this, so please.
Right. So, so today I'm talking about moving frames, and so we're continuing with the Lie group actions, and I've had lots of requests to give a talk on moving frames, which is something I know quite a lot about because I actually wrote a textbook on them. So because I know the material so very well, it's possible there are little gaps that you might want that I don't know are there. So please ask if there's something you don't like. So on Thursday is the sort of the grand finale of my series of 3 lectures in which I talk about Nodus theorem, smooth and discrete. And today, and I definitely use moving frames there. So this is kind of hopefully a nice gentle introduction to the whole idea. So, but I have a couple of mini applications today solving differential equations and difference equations that have a symmetry, and I hope that these are of interest to this audience. So yesterday we looked at the action of SL2 on the Riemann sphere, which looks like this. It's the Möbius action. And remember that we prolonged this action to derivatives using the chain rule, and this is what it looks like. So the first one you can probably do in your head, and after that I need Maple. Well, actually I think I did do that one by hand, but anyway. So, so what are we actually doing here? I'm going to solve. I've got these coordinates on my space, u, ux, and uxx. I'm treating those as kind of coordinates, and I have a curve in my space, which is the parameter with parameter x, and I'm going to solve for the group element, which takes ux and uxx to this point 0, 1, 0. In other words, I'm going to solve. So I've already got one equation on my 4 parameters because I'm in SL2, and I'm going to solve that the action on u is 0, so it takes u to 0, ux to 1, and uxx to 0. So if you just go back here, you'll see that I can't solve ux goes to 0. I can only solve ux goes to 1, and you can see that I'm going to need that ux is positive. Okay, so why am I doing this? Well, you'll see that this is a fabulous thing to do, I hope. In a sense, I'm saying that that provided ux is positive, that I can in fact map every point to this one point here. But what I'm going to develop for you is a very kind of intuitive and computational view of this modern Lie group-based moving frame. Now, the moving frame is associated with a Lie Cartan, but the ideas do go back earlier than that to Darboux and Cotin, and there's been many subsequent authors, such as Green and others, who developed Cartan's ideas in Cartan's framework, which is principal fiber bundles and very serious differential geometry. However, the modern Lie group-based moving frame is really free from it's essentially a frame-free moving frame. It has the same content for Cartan's examples, but for example, you can apply these things to discrete, as I'll show you. You can apply it to discrete objects, to piecewise smooth, I've even seen applications to statistical data. So this is a very much more general concept that can handle applications that Cartan could not have dreamed of. So let's solve our equations and see what we get. Well, this is what we get. So you can recall that I have my 3 equations, AU plus B. So you can see that A times U plus B is 0, yes. I can see here that CU plus D all squared is, I can see that CU plus D is the square root of U of X, and I've chosen this one so that and so on and so forth. And the main point I really want to make here is that this is a unique solution, and this uniqueness is really key, that I can solve those equations for a unique element of the group. And provided I have uniqueness, then I have a very powerful property, which you'll see on the next slide, which is, yeah, so why is this so marvellous? Well, it's marvellous because by uniqueness of the solution, I have if I take my curve and I act on it with a group element, if I act on it with a green group element, I get the green curve. And then if I supposing I now want to solve for the group element that takes me from here to here, well, by uniqueness, it has to be G inverse and that. It has to be the same. So what this means is that my map, which takes my domain, so M is the space on which the group acts, and by convention it's restricted to the domain of the frame. So it's by an abuse of notation, this is now the domain of the frame. So I have a map which takes me from my space on which the group acts to the group, which is equivariant. It satisfies this property. So the proof of this equivariance looks trivial, but when you see it in practice, it looks rather magical because what does the equivariance actually mean? It means that if I do this G dot Z, it means I just put a hat on everything, and miraculously it all unwinds just like that. So you can see that 1 over the square root of u of x, well, this is my equation, so 1 over the square root of u of x is cu plus d over the square root of u of x. And you can also see that u goes to au plus b, so that denominator cancels, and I'm left with this, and I hope that you can see a first few of it coming out, and I leave the rest of it to you for an exercise. So this is a feature of the moving frame theory, which is that the proofs are trivial, but the examples look completely outrageous. But nevertheless, it's guaranteed by general principles. All right. So why is equivariance so fantastic? Equivariance is the key to success in anything to do with Lie group actions. Why is equivariance so great? Well, let's keep going. Let's induce the action on higher and higher derivatives. So I can do that I just keep using the chain rule recursively. And now let's act on this, but now let's act on it with the group element, which is this frame that I've just derived, this very specific group element that I've arrived. And let's call that this I of u and x, I for invariant. So now let's get this. So G of this, well, this is the definition, I just put a G in front of everything. So now the equivariance means that this thing with the upper green bracket goes to that, the upper green bracket. That, of course, is just that. And now by the property of the group action, I can pull that through, and this cancels, and it's invariant. So what I have is that you give me a frame, I give you an infinite sequence of invariants of higher and higher and higher order. So that's already fantastic, that you have this infinite sequence of invariants. So, and indeed, if you do this to the third order invariant, to the third derivative of u, you obtain this, which is a very, very famous invariant indeed. It's the Shortsian derivative, and that's what you obtain. And in general, we obtain that the invariant associated with un plus 1 derivative is equal to the derivative of the previous one plus stuff. And the plus stuff turns out to be interesting, as you will see. The plus stuff turns out to be very interesting. Okay, so we have an infinite set of differential invariants, but actually what we have is a complete set. You give me any differential invariant at all, and it's a function of one of those. So let's look at the next magical property of the moving frame, which is called the replacement rule. And so in the Fels and Olver papers that developed this theory of moving frames, they credit this to somebody called Thomas. Okay. So, what is it? What is an invariant? Well, a function of these babies is an invariant if you put a g on everything, and it doesn't matter. Somehow, when you operate with this g and then you simplify, all of the parameters of the group disappear, and you're left with what you start. So what I have is that this is equal to this for all g. Well, if this is equal to this for all g, it's certainly true for the particular g, which is my frame. So, all right, my f is now equal to this, with now instead of g dot in front of everything, I have a rho dot in front of everything. But what are these? Well, x is invariant by my group action, so it stays the same. My rho sent u to 0, ux to 1, u double x to 0, and then this goes to that third order invariant, the Schwarzian derivative, and so on and so forth. And what I have here is I've written my f, which looks like this, as a function of my what's called the normalized derivative invariance. So that's the replacement rule. So this has two. So first of all, it means that my frame has given me a complete set of generators for my algebra of differential invariance. But provided I know that I can solve for for the frame uniquely, I don't actually have to be able to solve. Provided I know that in principle I can solve for rho, I don't actually have to have solved for it. I can still do this trick. I can still play this trick and view these things as symbolic invariants. And what this means is that if you have a very famous Lie group action with a lot of applications, there's going to be a lot of historically known invariants. And what this means is that you can obtain the historically known invariants in terms of your symbolic normalized ones. And you can then use, because I'm not going to show you, but there is a very powerful symbolic invariant calculus of invariance, and you can use that very powerful calculus even in cases where you can't solve for the frame. So let's do this. Let's have a little go. So if we take our Schwarzian derivative and differentiate it with respect to it twice, well, you just get a big mess. Yes, big mess in Maple. Maple's very good at creating big messes, and my job is to make them look nice. So if I use the replacement rule on my big mess, I get something very pretty like that. And so you can see here that the second derivative of my third order one is the invariantization of the fifth order one plus stuff. And that's kind of how it goes, plus invariant stuff. So let's make a little, I want to make a little application. So first of all, I note that because my independent variable is invariant, and then this operator is an invariant operator. And it means that this matrix, d rho by dx, that's not right. There should be a row. There's a row. It's meant to be a row of z there. Yeah, I changed colour and erased too much. Sorry. That's d by dx of rho of z times rho of g of z is that. And it's because this g doesn't depend on x, so you use the equivariance, you use the product rule, and the g cancels. In other words, this baby here is invariant. And this is known as a curvature matrix in the general parlance, and it is a matrix whose components are invariants. So let's look at what we have. Well, this is what it is. This is in the Lie algebra. Let's draw a little doodle-lucky. Thanks. So I'm in my group. Here's the identity. Here's my path in the group given by rho, and if I differentiate it and pull it back via the here, I end up in the Lie algebra. So the Lie algebra of SL2 is trace-free 2 by 2 matrices, and that's what I have. Okay, so why is this so great? Suppose we have an ODE, and this action induces a symmetry of this ODE. In other words, it maps solutions to solutions, and the order is greater than 3. Then I can write this as an ODE in my invariant V. So in order just to spare the notation, I've written this third order invariant as V. So I now have an ODE of order 3 less. And now I'm going to, so now what we have is a divide and conquer procedure for this one. You first of all solve the reduced ODE for V, and that's your problem. Yes? Not mine. And that's as far as the classical texts on symmetry analysis of ODEs takes you. They say, oh well, you solved that one for V, and then you're stuck because V is this third order invariant, and that you've got to solve now for this third order invariant, which is a nonlinear expression, is equal to some function of x. So that's not particularly helpful, but the frame allows you to keep going. So the new part of moving the frame means I now solve this. Remember, this is rho x rho inverse here. So I now solve this for rho. And so here we have an integration on the Lie group, and of course we have world experts on Lie group integrators here. But the next thing, so we've got rho, and the next thing of course is we know that rho acting on U is 0. So rho inverse acting on 0 is U. So what do I have here? Well, here's G, and so if G is my standard element A, B, C, D, then G inverse looks like that. G inverse acting on U looks like that. So G inverse acting on 0 looks like minus B over A. And that, so in other words, I have you give me rho, I give you algebraically U, which is the 1,2 component of rho divided by the 1,1 component of rho. And similarly, I don't have to differentiate this to get derivatives. I can do rho inverse of U on Ux, and da-da-da-da-da, and I have everything. I know everything about U, all for the price. So I've gone from a non-linear, so to solve the Schwarzian is a function, which was that non-linear expression. I've now, the frame converts that, is set to a linear problem. So this is good, yes? That's good. Alrighty, so now suppose our curve evolves in time, and I'm always taking the same action so that you can, so now of course the same method gives me that and I take my time to be invariant, so I get this, I get all of these derivatives, new derivatives, and I get new invariants with the same rho. And if I use this same rho, then the invariantization of ut is ut over ux, and so on and so forth. And this action is the one that's appropriate to each derivative component. So we have that not only is rho x rho inverse invariant, but also rho t rho inverse. And if I work this out, then I get this, where w is this ut over ux, and v is my third order Schwarzian derivative invariant. I have that. So this is my second curvature matrix. And these matrices must satisfy a compatibility condition. So this is the standard 0 order curvature condition, because I have matrices of the particular form. So because this matrix looks like that and this matrix looks like that, when I actually do the d by dx of one minus d by dt of the other, I actually get the commutator, which is like that. That's a very easy computation. And what I get, there's only one, when I do this calculation, there's only one non-zero component, and it is that. That's what it is. So in other words, so remember V is a third order invariant with U xxx, and W is a UT over UX. So what this says is if I differentiate V once with respect to time, and I differentiate W 3 times with respect to X, I'm going to get on the one hand, I'm going to get on each side a UXXXT over UX. So they cancel, and all of the stuff, this is all of the remaining stuff, and this is invariant. Now there will be some people here who know what this operator is. It's a very famous operator. Chris Budd should know what it is. He had it on his slide. It's the Korteweg-de Vries operator. Yes, yes. So
it's one of the KDV operations.
yes, yes. It's the lowest one. Yeah, yeah. Yes. So let's have a little fun. Let's do a little mini application with KDV. So we're going to use the syzygy on Thursday to ease the computations for variational problems with this Lie group symmetry. But for now, I want to do a little mini application, which is we're going to see how to look at this particular PDE. So this has got a name. It's the Schwarzian KDV. There's my Schwarzian, my third order invariant, and here's UT over U of X, and this is W equals V in terms of our invariance. All right. So writing it in terms of the invariance hasn't done a great deal so far. This is the difference between ODEs and PDEs. Yeah.
Are you accepting questions or not?
Yeah, yeah.
Is there any question?
Ask your question.
On that slide before you mentioned curvature, but where's curvature? So
Look, if you set this all up as on a principal fibre bundle and mosey along, then you do get a curvature. So it's called curvature because of the wider area of mathematics in which it sits.
okay.
Yeah,
I get it.
yeah. So we've just used that terminology in order for people to see that it's the same thing.
I had another question.
Yeah.
So you use the word frames. Frames are for me 3 little vectors. But
Yeah, yeah.
You mean something different? Or you mean the tangent vector? Or you mean, whatever you mean? Then I understand you.
That's a very good question, and I'm very happy because I have an answer which you'll like. So, we're in XU space, and my group, I'm going to do my group is this special Euclidean group, yes, and I have my point and Cartan's frame. So what's a good colour? Yellow. Okay, so that's Cartan's frame, yes? Cartan's frame is the orthonormal. That's the tangent, unit tangent, and the unit normal. All right. That's. Oh, I haven't drawn it. I've drawn one parallel. It's terrible. I have to change it. You won't get that. You won't get it. I have to draw I have to draw it at a better angle. Right. So here's the unit tangent, and E2 is the unit tangent. All right, that's Cartan's frame. Is simply this unit tangent and unit normal moving along the frame. Are you happy with that? We're in the special Euclidean group. So, what is the same content of the modern Lie group-based moving frame? So the equations that you would solve. So then what is the modern frame? The modern frame takes equals r of theta. No. Let's do it like this. All right, that's the action. Rotation and translation. I'm going to take the translation to there. That's the translation is back to the origin. Yep. And I'm going to take the let's just put that there. And if I take the rotation back to the parallel that, so Cartan's frame is equivalent to the Lie group-based moving frame if I solve and has the same content, has exactly the same content as Cartan's frame. Yep.
You had x hat equals 0 or 1?
Flat, so 0. I translate the curve at that point back to here, and then I rotate it so that the slope is 0. You can do it to any number you like. Yeah. Okay. Does that answer your question?
Yeah.
Yeah. And that gives you a right equivariant frame. If you take it the other way, the inverse, you get a left equivariant frame and the equivariance looks different. And there's a mirror image, mirror worlds of left and right.
Yes, I will ask. So when you write ux over the norm of ux,
No.
does it mean 1 comma ux over the norm of 1 comma ux?
Yes, yes, I do. Thank you. Thanks. Thank you. Yeah. It's not relevant, but you get the idea. Okay. So so where were we? We've got our Mobius action, and we've got two curvature matrices with our frame, and the syzygy looks like this, which is a famous operator in the syzygy. So we're looking at the Schwarzian KdV, which looks like W equals V in terms of our invariance. So unlike for an ODE, with the PDE, when we write it in terms of invariance, we don't get much. But what we do actually have, we have the syzygy as well. So our equation is W equals V, and then you add in the syzygy, and what this means, of course, is that V satisfies quarter-vector-Riesz equation. So if you have the Schwarzian KdV in terms of U, then the Schwarzian derivative of U is a solution of KdV. All right. So now we can play the same game as we had before. So up to there, V satisfies KdV was known. But we can now go further because we've done all of this using a frame, and we have these curvature equations, these curvature matrices. I now have two compatible equations for the frame. This is a coupled system which is compatible. And as before, once I've solved for the frame, I can write down U and all of its derivatives algebraically in terms of the components of the frame. So this is for me this for me is a huge application of the Lie group integrators. Being able to use them in a compatible way, which I've looked at with a student of mine, and we have some results there, is important. So, smooth moving frames solve many problems. So Oliver and his group have done a lot. I've written a textbook and done variational calculus. I've done stuff with Gloria Mari Beffa. Eveline Hubert is here, did all of the rigorous development of the algorithms involved in the symbolic invariant calculus, amongst other things, amongst other applications. We have precise formula even when the action is non-trivial on the independent variables, and the theory extends far beyond the simple things on differential invariance that I've shown you. You can exactly the same mechanisms give you invariant differential operators, invariant forms in exterior calculus, invariant integral expressions and discrete invariants, and as long as you can define a frame, as long as you can by some mechanism, then you have all of this, and you have very powerful symbolic computation algorithms that allow you to do quite a lot just from knowing that you have a frame in principle and the equations that the frame satisfies. So until quite recently, the only guarantee that we had that a frame existed was to check the conditions of the implicit function theorem in those equations for the frame. But recently, with my former student Anna Rocker, who's here, we extended it to be able to use it for frames defined by a differential equation. In particular, we worked on the rotation minimizing frame, which satisfies a differential equation. And I believe Peter Olver's latest student, who's just graduated, also has an a further definitions of more situations in which you can define a frame other than using algebraic equations. So let's go discrete. That's the smooth. So let's look at we want to look at now difference equations and difference variational complexes. So what I'm going to do now is I'm going to have a much simpler action, which is simply scaling and translation. And this is a matrix representation. So this is a semi-direct product. This is the matrix representation that you need. And I'm going to make a frame which sends the 0th one to 0 and the first one to 1. And if you do that, you get this frame. All right. So remember that this part is the scaling part, and this part is the translation part. So what are my invariants? Well, I can take my frame and I simply have to operate on all of my other objects that I have lying around, which happens to be U2 and U3 and maybe U minus 1. And so if I actually do this, I always get this. So you can see that I'm subtracting off U0 and dividing by U1 minus U0 as I go along. So my invariant corresponding to UN is UN minus U0 over U1 minus U0, and this is obviously translation and scaling invariant. And by the replacement rule, I can take an arbitrary one of these and just use the replacement rule, and there it is. And I'm hoping that you can eyeball that really is. I chose a very simple action so that you could eyeball this. However, this is, you can see I've got the opposite to a smiley here. If I take this a 5th order invariant, the order 5, 1, and I shift it, well, there's the invariant. And what's this shift map? Well, it just means I add 1 to every index in sight. But this doesn't commute with this invariantization. If I look at the invariantization of U6, I get this one here, and this doesn't relate to that at all. Well, it does via the replacement rule, but so what do I get? So recall that for my differential invariance, I had this very nice feature that if I differentiated one of my invariants, I did get the next invariant up, but plus stuff. But this was a beautiful formula, and we love this formula. However, here we have a function of the other invariants, which is just way too complicated. It's a way too complicated a function. So we want something that's, we need a mechanism, we need to get around this in order to have, for the applications, recurrence formulae and differential difference variational complexes, we need to have something which is much better adapted to the shift operator. And Gloria, Mari Beffer and myself, and then we teamed up with Jingping Wang, who's my colleague at Kent, looking at some of the applications, was we simply took a discrete frame as an index sequence of frames. And you'll see that this does solve the problem. So a difference frame is a sequence of frames such that the shift of the frame is the next frame. And now we have beautiful formulae. If we do this, we have absolutely stunning formulae. So now I put an I naught on things because I'm going to use the 0th one. So now now the shift of row naught acting on U5, which is this, well that's row 1 acting on U6. But this row 1 acting on U6, I can give myself and take away row naught. Yes, by the group action. So this is the old one that I know and love. So this is the relationship between the shift of this one and the invariantization of the shift is now just simply this group action here. And you might say to yourself, but this is an invariant and this is in the group. But what it is this is a rewrite rule. I've got my invariant, but I'm writing it in terms of other invariants by using this matrix here. So this gives me recurrent. So if I have a discrete frame, a sequence of these things, then I do get beautiful recurrence formulae that take the shift of the invariant, that connect the shift of the invariant to the invariant of the shift. Yes. And so, so what does it look like? Well, it looks like this. And from this very almost naive observation that I have formulae like this, I can now build up a very strong theory to do with the symbolic computation of differential difference invariants, and I can manipulate them equally successfully in a symbolic computation environment is what I call the differential ones. So the trick was to have the sequence of frames and this baby here, and just to compare the outlines of the the very bare bones of the two theories. In the smooth case, I only need a single frame. The algebra invariance is generated by components of the curvature matrices and some pre-known outliers. And the algebra of syzygies is generated by the components of my zero curvature condition and known outliers. On the other hand, for the difference case, I have a sequence of frames. The algebra invariance is generated by the components of this one here and their shifts and some known outliers. So this is a theorem that you can get everything, and all of the local syzygies, or if you've got shifts in more than one direction, I go around a little square and they generate my different syzygies. Yeah, so I've got a bit of time left. So I thought I would talk about something a bit different. one of the big challenges in that we have in all of the various applications is to get is to find a discrete frame which converges to the smooth frame, because you're looking in your approximate space. You've got an approximate Nernst theorem, or you've got an approximate syzygy, or you've got an approximate integrable system. So they're the two big applications to date, and you want to find a way to guarantee convergence. So you want to design your frames. So one of the big things to do is to design your frames, because given that you have a lot of choice in these frames, the frames solve equations, and you can choose those equations to suit your application, if and only if, but always providing that you get this unique solution. So this is a very different, this is one way that Gloria and I looked at to obtain we're looking for have guaranteed a priori convergence. And what you're going to see in this next 5 minutes or so is something that could be greatly improved by people who understand approximation theory better than me. So this is an opportunity. And tomorrow, on Thursday when I do Nernst theorem, I will show you another much more naive method. So this is the sophisticated idea, and you'll see something much more naive. And naive is great, yeah? But sometimes you want to have something sophisticated just for the hell of it, yes? Just to say you did it. Alrighty. So this is Lagrange, Hermite, and Taylor approximation. So hopefully this is very familiar. I assume this is very familiar to everybody here. So the Lagrange I have a curve on 3 points, and I have a plane which goes through my 3 points in 3 space, and that's the Lagrange interpolation. If I coalesce 2 of my points in a nice way, I will get the Hermite approximation, and this means that my plane has 1 line and 1 point, and that line is the tangent line in the direction of coalescence. And then, of course, if I coalesce that with that, I get in a way that's transverse to that line, I will then get the Taylor approximation, which is, of course, the tangent plane in this particular case. So that's well known to everybody here. I'm just bringing that web page in your mind to mind. Yeah. Okay. So now this slide is possibly a little scary, but let's have a look. So one of the ways of defining a tangent space, if you don't actually have differentiation to hand, if the coordinates are too ugly, I mean, on a manifold you can always differentiate a curve in coordinates to obtain a tangent space at a point. But there's a much more subtle way to do it, which doesn't rely on which is coordinate free. It's a coordinate free definition of a tangent space, which is that you have equivalence classes of curves going through a point, and 2 curves are equivalent if in coordinates they have the same derivative. So you can generalize this notion to the jet bundle of order R. So here, this is Morris Hersh's definition of a jet bundle, and I think this is I guess quite an old textbook on differential topology. I think it's absolutely brilliant. I love this book. Anyway, so what we have is a coordinate-free definition of the jet bundle, which is the equivalence classes. There's the point, there's my function, there's the domain, a little domain about x. And I have equivalence classes, and it's set up so that each equivalence class, the equivalence class up to order R, f is equivalent to its Taylor polynomial evaluated at that point. So this is a flash way of defining a jet bundle, and it's this and this was the key to being. So what we're trying to do, what am I trying to do? I want to have the jet bundle and the discretization all in one manifold. See, I've got beautiful theories for frames on manifolds. I've got smooth theories, smooth frames, I've got discrete frames. I want to have if I had a space which had both the tangent space and the approximations around it in one manifold, and I define because I can always induce the Lie group action on the approximation data. This is the big thing. If you so you've seen how to induce the action on tangents and higher derivatives simply by the chain rule. And there's ways and means of inducing actions on moments. I'll talk about this on Thursday. But this is quite a well-defined process. So if I have both the tangents and the nearby local approximations of my functions all in one manifold, and I have the Lie group action well defined on the whole thing, and I can define a frame on that, then because the frame is a smooth function, I have a smooth link between the frame on the approximations and the frame on the tangents, just simply by continuity of the frame, because I'm in a bigger manifold, etc. So the whole kind of big. So the game plan here is simply to expand the jet bundle and add more dimensions on each fibre, which includes all of my approximations. So at the moment we could only do it for Lagrange, Hermite and Taylor, but I'm sure that people here can do better. So we view the Taylor polynomial as a coalescence limit of the Lagrange interpolation of a function on a lattice, and this process requires an appropriate lattice and a very well controlled coalescence process, because you can't coalesce on curves wrapping infinitely around a point. You know, it has to look good. So we take things that look like corner lattices. So these lattices have to have the right amount of data to construct an approximation to a certain order, and we have and we have to have a base point, because our multispace because I'm looking to generalize the jet bundle, and jet bundles have base points. They have a projection from the bundle to the base manifold, and there's that projection, so they have to respect our big new bundle has to respect this projection. So they have base points. And so this is a standard lattice, but there's plenty of others that you can do, and these lattices, there's a rigorous definition for them, and they're guaranteed to work. Okay, and we also have to have a very well-defined coalescence. So essentially what I have is that this baby here has to go to that baby, and that whole line has to go to has to go in a well-controlled way to that line. We formulate this rigorously, and we call it hyperplane coalescence, so that we get this very well-defined limit from our Lagrange interpolation through to our Taylor polynomial. So the notion of a lattice includes the set of contact conditions to be satisfied by the function approximation, and these conditions must be well defined under coalescence. So that's all set up rigorously in this paper. So what do I have? Well, I have my lattice, no, that's the lattice, that's the thing where it's domain, that's the point, the base point. And so I have my lattice in my U. This is my coordinate chart, sorry. Look, this looks like a coordinate chart in M, and I have this, and my equivalence classes. So what do I have here? Well, my functions have to agree at a point and have the same derivative at that point. So so we have these equivalence classes from F to F prime, and the contact conditions on the lattice must equate to 0. That's kind of the equivalence condition. Okay, what are my coordinates on my multispace? Well, a function defined on the plane with values at 3 points has this interpolation. So this has 6 coordinates: x0, x1, x2, f of x0, that baby there, and that baby there. And they're my coordinates on my. So these are the coordinates that are defining my bundle as a manifold. And if I coalesce, well, I have that coordinate twice, and then I have f of x0, this baby, and that baby. So even under I don't lose coordinates under coalescence if I maintain multiplicity. Alrighty. So the proofs rely on results by Karl de Boer and Amos Ron. And this is the paper here. This is a fantastic paper. There's 3 papers actually, and they're absolutely fantastic. And they have a huge variety of functionals under which you can obtain multivariate approximation, and because there's various problems you have to, I mean, it's not in general well defined, but they give conditions and they show it's constructible, and in the end, and they show that, well, I can totally recommend this paper if you've not already seen it. It's really brilliant. Okay, so we designed the multispace to solve the problem of coordinating moving frames on smooth curves and their discretizations. And so the whole aim now is to extend the Lie group action to the new coordinates, and that in other words extending it to the approximation data. And I've got a little example here to show you. So if I take again the scaling and translation, and it's a semi-direct product. So the induced action on the multispace is that the lattice points are fixed. So now let's look at these. If we now look at the coefficients of x minus x naught in the first order interpolation, so what is this? Well, x naught and y naught are fixed. It only operates on this u naught, and it comes out as a scaling. And this is evidently consistent with the induced action on derivatives calculated via the chain rule. That doesn't always work out that pretty. But it does here. That's why this one's on the slide, because it works out nicely. Yeah. Alrighty, so if I continue, so now it's not so difficult. So if I continue with this, on this lattice, then the action on here is that this is the action on this coordinate, this is the action on the coefficient of x minus x naught, and this is the action on the coefficient of y minus y naught. So I have now I've got a well-defined induced action on my approximation data, which is this goes through under coalescence to the induced action via the chain rule. So I now have this wonderful coordinated Lie group action, and I can now make a moving frame. I've got a 2-parameter group, so I only need 2 equations. So I'm going to send this one to 0 and that one to 1. So this now is my moving frame. That's the scaling part, and that is the translation part. And I can go through and I can make myself some invariants. So I've now got the freedom to do everything I could do before. I can make invariants, I can make differential invariants, I can obtain curvature equations, I can obtain syzygies, anything that you want you can do, because I've got the frame. So depending on whether the coefficient is determined by the grid being 3 distinct points or a single point with multiplicity 3, in which case it either looks like a quotient of determinants or is a derivative expression, the frame will be either in terms of the Lagrange discretization or in terms of the Taylor coefficients. So this expression for the frame simply shifts from being on the standard jet bundle or to involving the approximation data. And the whole point is that I have simultaneously a smooth frame and a discretized frame, and I'll show you, and equivariance is maintained. So that's very important. So here I've simply calculated for you what is this invariant here. If I act on B and calculate the invariant, that's what I get. I get this. And I get this, and if I do the coalescence, I get that, and that is the relevant invariant on the embedded jet bundle. So finally, this is my final slide. It looks discrete because I can take the frame at one point and the inverse of the frame at another point. And that's kind of like my discretized frame where I had a sequence of frames. So now I just can have frames at various, I can construct a discrete frame simply by taking the frame at various points. So these things are my discrete invariants. They look like discrete invariants, and when I coalesce under a well-defined way, I pick up the smooth curvature matrix in a well-defined way. So in other words, my discrete Moore-Cartan invariants limit to the differential ones, and the discrete local syzygies limit to the discrete differential syzygies. So that's the landscape. It's an opportunity for I have to say that the invariants that they give you aren't very nice. It would be really nice to have a better bundle, maybe with application, coordinates dependent on the application that are of interest to the people working in it. Anyway, that's my jet plane flying over moving frame land. And I hope it gave you an idea that this is an interesting theory and that might be of interest to you. Yeah.
Thank you. Questions?
So, this coalescence,
Yeah.
what are the conditions that makes it a good coalescence? What is it that you need?
You need coalescence along curves that don't oscillate around. So they're curves with a well-defined derivative, and there has to be certain transversalities in how the different things. You have to maintain this transversality. Yes.
That's your condition, but how does it translate? So I guess, okay. So you have your interpolation polynomial, and somehow you want to have it approximate the Taylor expansion of.
Yeah.
So in terms of these two things, of the interpolation polynomial and this Taylor polynomial, can you express this coalescence in one converging to the other, or?
Yes, it's sort of like you've got a one-parameter family of lattices. So you have a one-parameter family of lattices designed such that the coalescence is well-defined, such that the limit is well-defined from one point to the other. It's essentially...
And it's on these two polynomials that you're looking at this convergence.
Two polynomials.
I mean, this Lagrange interpolation polynomial
and the Taylor polynomial. Yes, and the seeing is believing. Yes. Yeah, it's essentially a path in the space of lattices and under which the limit is well defined. You get what you want.
So, if I may.
So it's not just the points of the lattice. It's the contact conditions that the equations that the approximation has to satisfy. So if you have interpolation at 2 points and they come together on a well-defined path, then you will, with a proper tangent at the point where they come together, then the approximation goes from equality at those 2 points to equality at the one point where they meet and a derivative condition.
So what pops to mind for me is that this the least interpolation space for both problems, as defined in this the board paper, is the same.
I think we should discuss this later. Yes, if you've read the De Boer paper, then we can discuss it. But I mean, I think that paper is a considerable achievement, I have to say, because this is multivariate interpolation is not an easy problem, and they do show how to solve it.
On the note of discussing things later, I think we now have a morning coffee, so that's a good opportunity. So let's thank listeners again.